Hello everyone, welcome to my second video for my Capstone project. Today we'll be discussing chemical equilibrium. So let's begin with the idea of reversible reactions. So as you know, reactions go forward, but they could go backwards, or they could just not go at all. So for example here, a spontaneous reaction would be when reactants go towards the products, and 99.9%, like almost all of it, would become products. Otherwise, a non-spontaneous reaction would stay as reactants. So more than 99% would be reactants, and you would barely have any products. That's non-spontaneous. But in equilibrium, both the reactants and the products could be favored. So you could have both. It looks like this. Or you could draw a double arrow like this. It's easier. Yeah. But what is equilibrium really? So when a chemical reaction is in equilibrium, both the reactants and products are favored. And then the important part is the rate that the forward reaction is happening is equal to the rate of the reverse reaction. So the products are being made, going this way, products are being made at the same rate as the products are going back into reactants. So write that down. Forward rate is equal to reverse rate. And because you're going forward the same rate as you're going backwards, their effects kind of cancel out. So you don't really see any changes in macroscopic properties, such as like concentration. Because of all of this, for a reaction to be in equilibrium, it needs to be in a closed system so that the products could actually go back into being reactants, or the other way around. It has to be reversible. There has to be no change in macroscopic properties. And finally, the temperature has to be constant. Let's look at an example here. So here I have a beaker with water in it. And what I'm going to do is I'm going to add salt. Okay, so I'm adding salt, and then it dissolves until it can't dissolve any further. And then I have a whole clump of salt sitting at the bottom of my container. So at this point, it's called a saturated solution when you can't dissolve any more substance at that temperature. So I'll have just some solid salt floating around, or like at the bottom. And then in the environment, I have my ions. So as you know, salt and NaCl would dissolve in water to become Na plus and Cl minus. So that's what these red dots are. They're the dissolved salt. And what's actually happening is, in a saturated solution, this is called solubility equilibrium, by the way, but we'll touch on that on another video. But what's happening is that the ions are precipitating into the salt at the same rate that the salt is dissolving into ions. So your solid is actually in equilibrium with your aqueous ions. The ions are becoming the solid, while the solid dissolves into its ions at the same rate. So there's a constant back and forth here, but you won't be able to see any actual changes because they're going at the same rate. So that's what it means to be in equilibrium. Now let's consider this reaction again. Just reactants in equilibrium with the products. So let's say you started out with only reactants. Then what would happen? Well, initially, if you only had reactants, you wouldn't have any products at all. So the rate that the products turn back into the reactants is 0. So I could say the reverse rate is equal to 0. But because I know the reactants will turn into products, my forward rate would be something. It would exist. So my forward rate is going to be greater than my reverse rate. So what happens is the reactants are going to turn into products. And as that happens, the reverse rate will start going up until they're equal to the forward rate. And then it'll be an equilibrium. So this graph is reaction rate over time. So let's first look at our reactants. That'll be my purple line. So the rate will start up here, and as the reaction proceeds, it'll go down. Now my red line is going to be my products. So initially I don't have any products, so it's going to start at 0. But as more of it is going to be made, the reaction rate will keep going up until it becomes equal to the rate of the forward reaction. And then now it's in equilibrium. Now let's look at two factors that control equilibrium. The first one is enthalpy. So remember when we learned about exothermic and endothermic reactions? So for example, I have my two potential energy graphs here. For my first one, you can see it goes from a lower to a higher potential energy. So that means it absorbed energy, meaning this is endothermic. And on the graph on the right, we see that it goes from a higher to a lower potential energy. So it released heat or energy. So this one is exothermic. Now the difference between the two potential energies as the reaction progresses, that's known as your delta H, or your enthalpy change. So this is delta H, and so is this. It's also known as the heat content. So if we look at the first one on the left side, the endothermic reaction, we see that it goes up, right? So our change, our delta H, is going to be positive. And on the right side, it goes down. So it's going to be negative. So why does this matter? It's because reactions, they tend to favor exothermic reactions. Those are usually the spontaneous ones. In other words, there's a tendency or a drive for reactants to achieve a lower enthalpy, which is why exothermic reactions are favored, because they go to a lower enthalpy. Their delta H is negative. Now let's look at these two reactions. We need to figure out if it's exothermic or endothermic. So let's look at the first one. We see that the heat term is on the reactant side. And that means that you need to put in heat for the reaction to proceed towards the products. So because we're putting in heat or energy, that's going to be endothermic, which means our delta H is positive. And our second one, we see that the heats are in the products. So as the reaction proceeds and you make product, it's going to release heat. And because you're losing heat, delta H is negative, and it's going to be exothermic. Now let's talk about entropy, or delta S. So what this is kind of a measurement of chaos or disorder. So for example, if we look at this diagram, we have a gas, a liquid, and a solid. And looking at it, we can tell that the gases is more disordered than, for example, the solid. The solid, all the molecules are packed together and they're often structured. So every molecule has its place. But if you look at the gas, the molecules, they just want to expand and fly everywhere. They're all moving in different directions. That's very chaotic, you could say. So that's why a gas has a higher entropy than a solid. And for a liquid, you can see it's not as entropic or chaotic as the gas, but it's still a little bit more disordered than a solid. So a liquid would be kind of in the middle in terms of entropy. But how about aqueous solutions? Well, because an aqueous solution has ions inside of a liquid, that's more disordered than if you had just a pure liquid. An analogy would be having a room full of people that are exactly the same height, that's being liquids, or a room with a bunch of people who are the same height, but you have like 10 people who are like extremely tall. So that's a little bit more disordered than when you have a room full of similar heighted people. So that's why aqueous solutions are more entropic than liquids. So to rank them, the highest entropy is gas, which is much more entropic than solutions, which is a little bit more entropic than liquids, which is much more entropic than solids. And similar to enthalpy, reactions have a tendency or a drive to achieve a higher level of randomness or chaos. So reactions where entropy becomes higher as you become products, those are more likely to be spontaneous. Let's look at this example. We want to figure out if entropy increases or decreases when you go from the reactants to the products. So looking at this, the way to tell is to look at how many moles of each thing we have. So on the left side, we have 2 moles of gas. 2 moles gas. And on the right side, we have 3 moles of gas. So 3 is more than 2. So we know that going from reactants to products, you are achieving a higher level of entropy because more gas means more disorder. So in this case, delta S is positive. Now let's look at this reaction. We can see that on the left side, we have 2 moles of gas. But on the right side, we only have 1 mole of gas. So when we go from reactants to products, we're decreasing the amount of moles in the reaction. So that's actually going to be more ordered or less disordered, which is why our entropy is negative in this case. So to recap, reactions have a tendency to go towards a lower enthalpy, so exothermic reactions, and they have a tendency to achieve a higher entropy, so more disorder. But what if you had a reaction where enthalpy and entropy are both at play? So what happens then? So our first case here, we don't know which way this reaction will proceed, so I put a question mark there instead of an arrow. So let's look at the enthalpy and the entropy. First, we see that the heat term is on the right side, so it's in the products, which means that this reaction is exothermic. Now let's look at entropy. So looking on the left side, looks like we have 2 moles of liquid and then 25 moles of gas. Now on the right side, we see that we have 34 moles of gas. So looking at it, we know that 34 moles of gas is much more disordered than 25 moles of gas plus 2 moles of liquid. So we know that going towards the product side, that's increasing entropy. Okay, so what we have now is delta H is negative, and then delta S is positive. So because delta H is negative, that's exothermic, we know that the reaction would tend towards the product side. And same with entropy, it increases. So the reaction will drive towards the products. So we know that this reaction is now spontaneous. So I could draw a forward arrow. Now for our second case, let's look at this example. So if we look at enthalpy first, we see that the heat term is on our left side. It's on the reactant side. So this reaction is endothermic. Endothermic, so delta H is positive. And that tells us that in terms of enthalpy, the reactants will be favored. But now let's look at entropy. We see that we have 4 moles of solid on the left side, 3 moles of gas, and on the right side we have 2 moles of solid. Because we have a gas on the reactant side, that's already much more entropic than a solid. So we know that going towards the products, that's decreasing in entropy. So delta S is negative. And that also tells us that it'll drive towards the reactant side. And from this, we know that this reaction is non-spontaneous. So I'm going to delete this arrow and put a backwards arrow. Non-spontaneous. Now for our last case, let's look at this. In terms of enthalpy, we see that the heat term is on the product side. So it's going to be exothermic. So delta H is negative. And that means that in terms of enthalpy, it will drive towards the products. However, let's look at entropy. We see that we have 2 moles of gas on the left side and only 1 mole of gas on the right side. So our entropy is actually increasing. And that favors the reactants. So if enthalpy wants the reaction to be spontaneous, but entropy wants it to be non-spontaneous, which one wins? What happens? So in this case, there could possibly be a reversible reaction, or an equilibrium could be established. Now I'd like you to consider what would happen if we have a reaction in equilibrium, and then I added. Now suddenly the forward rate is going to be greater than the reverse rate, because as you learned from your kinetics unit, increasing concentration also increases reaction rate. So then the forward rate and the reverse rate aren't equal anymore. So the equilibrium has been disrupted. So now we're going to learn what will happen and how the equilibrium will be reestablished. Let's begin with Le Chatelier's principle. It states that whenever a stress or change is applied to a closed system at equilibrium, the system will tend to respond to reduce the stress or change and establish a new equilibrium. So think about the example I told you earlier. So when you increase the concentration of the reactants, that's a stress. So what the system's going to do is it's going to try to counteract that stress. How does it do that? It's going to make more products to get rid of that excess reactant. Now this principle is actually a shortcut. It doesn't actually explain why the system would shift a certain way, but I'll get to that later. So let's look at different things that could happen to a system in equilibrium and how it will respond. Okay, let's look at what happens when we increase concentration of something in an equilibrium. So let's look at this example here. I have green, which is in equilibrium with red. That's just a random example. So as you can see, the concentrations are constant. They're not moving. So they are initially in equilibrium. But let's say at this time right here, I added more green. Okay, so the concentration of green is going to go up at this time. And then the concentration of red stays the same. So think back to Le Chatelier's principle. Increasing the concentration of green, that's a stress, right? So how do we counteract that stress? We're going to make more products to get rid of the green, to react it out. So if we make more products, so we're going to be making more red. So the concentration of red is going to actually go up, while the concentration of green will go down. So it'll look like this, and then the concentration of green will go down. And if we look at our initial line, we still have more green than initially, but less. And then as for red, we actually have more than what we started with. And now a new equilibrium is established. But instead of Le Chatelier's principle, let's see what actually happens. So when I increase the concentration of green, we know that the forward reaction then becomes greater than the reverse reaction because the reverse reaction doesn't change at that time. So here I'm going to say forward reaction rate is going to be greater than the reverse reaction rate. And because you're making products faster than you're going backwards and making reactants, you're going to end up making more products as a result, which is why at the end you're making more red. And then as you make more red, the reverse rate, which the red becomes green, will also increase. And then eventually they'll balance out and establish a new equilibrium. Now let's look at what happens when we change the pressure or volume for an equilibrium involving gases. So in this example, I have two green gases, and that's in equilibrium with one red gas. And at time A, let's say time A, the volume of the container was decreased. So as we know, decreasing volume would then increase pressure, and then meaning concentration for all gases. So at time A, both the concentration of green gas and the red gas will increase. So let's label this top one as green, bottom as red. And they both increase at time A. But if you look at the reaction here, we have 2 moles of green gas reacting to form 1 mole of red gas. And because there are more gas molecules on that side, it's going to be affected more by the change in pressure. So the concentrations actually go up even more. Okay? And at this point, you have more green than you have red. And that disrupts the equilibrium. And as a result, at time A, the forward reaction is going to be greater than the reverse reaction. And as a result, the green will go down while the red goes up. And all this is to remove the stress of the extra green concentration. It's to decrease it and establish a new equilibrium. Now let's look at what happens when temperature is changed in an equilibrium. So we have this reaction again. We have green in equilibrium with red. This time it tells us that delta H is positive. So this is going to be endothermic, going towards the product side. And let's say at time A we increase the temperature. Now we know that increases the reaction rates of both the forward and reverse reaction. However, the rule is that the endothermic reaction is always affected more by changes in temperature. And because we know the forward reaction is going to be the endothermic one, that's going to be affected more by temperature. So increasing the temperature at time A would increase the reaction rates of the forward and the reverse reaction, except the forward reaction will actually be greater than the reverse reaction rate because the forward reaction is endothermic, so it's affected more. So at time A, the forward reaction rate is greater than the reverse reaction rate. And as a result, there'll be an equilibrium shift to make more products. So it will look like this, it'll go down while the products go up. A tip that I found useful is that when you write out the forward and the reverse rates, if I say the forward is greater than the reverse rate, I draw this inequality arrow, right? And it's facing the right. So I know that it'll shift towards the right side. If the forward rate was less than the reverse rate, I know that there'll be an equilibrium shift to the left side, making more reactants. Finally, let's look at what's called the equilibrium constant, KEQ. And in a reaction, let's say this reaction, where the small letters are the coefficients, the KEQ is the concentration of the products to the power of their coefficient over the reactants, or the concentration of the reactants and the products to the power of their coefficients. So what this shows, it's like a mathematical relationship, or like a ratio of the concentrations for a reaction at equilibrium at a given temperature. So in other words, at a given temperature, and you have a reaction at equilibrium, the concentrations of each species could be big or it could be small. But the ratio between how much you have once equilibrium is reached is the same, considering you don't change the temperature. Now here's something very important, and I got this wrong in the test too. So temperature is the only thing that affects KEQ. Anything else does not affect it. So make sure you know that. And also, because if we look at this KEQ expression, they're all concentrations, right? So liquids and solids, they don't have concentrations. So they're never included in KEQ calculations. Let's do an example. So here's an equilibrium reaction. And it's telling us to write out the equilibrium constant expression. So first, we know it's products over reactants. So we look at our products here. We have NO2, so concentration of NO2, and we make sure to raise it to the power of its coefficient. So this one has a 2, so it's to the power of 2. And it's going to divide it by our reactants. So we have NO, make sure to square it, because the coefficient is 2, and then concentration of O2. And this is equal to KEQ. Okay, let's do another example. We have A2. So in this case, we have a solid on the right side. So we know that isn't counted in the calculations. So we just have 1, which is our products, divided by our reactants, which is going to be concentration of A2 times the concentration of B2. Now, because KEQ is products divided by reactants, a very high KEQ would suggest that you have lots of products and not as much reactants. Because if the products term was very big and the reactants is very small, then that's a bigger fraction, right? So that means the products are favored. Otherwise, if KEQ is very small, you know that you have lots of reactants and not as much products. So when your denominator gets bigger, then the fraction itself gets smaller. Now let's try calculating KEQ. So in this equilibrium here, it tells us that the concentration of CO2 is 0.16 molar, the concentration of H plus is 0.38 molar, and the concentration of HCO3 minus is 3.0 molar. Now let's start by writing out the expression for KEQ. So that's going to be our products, the concentration of our products, HCO3 minus times concentration of H plus divided by our reactants. So we have concentration of CO2, and we don't write the concentration of H2O because it's a liquid and there is no concentration. Okay, so now we can just plug in our numbers. So it's 3.0 times 0.38 over 0.16. And plugging into a calculator, we should get 7.1. And that's our KEQ. Now let's look at this type of question. It tells us that in this equilibrium, there's initially 0.70 molar of PCl5. And then that's before equilibrium was established. So that's like, I just put that much PCl5 in a beaker and I let it react. So that's how much there was initially. And then once equilibrium was established, we have 0.15 molar of Cl2. And we're trying to find KEQ. So what we have to do here is to do what's called an ice table. So I'll move these to the side. Ice. And what this stands for is I for initial, C for change, and E for equilibrium. So E for when equilibrium is reestablished. So let's fill in what we can right now. So we know that we start with 0.70 molar of PCl5. And we know that we don't have any products right now. So these are going to be 0. The change, we don't know yet. But what we do know is that at the very end, so once equilibrium is established, we have 0.15 molar of Cl2. Okay. And now we can find the change because we went from 0 molar of Cl2 to 0.15 molar. So I'm going to write plus 0.15 there. And because there's a 1-to-1 ratio between the two products, it's going to do the same thing. So they're both going to go up by 0.15 molar. And because it's also a 1-to-1 ratio with the reactants, it's going to minus 0.15 molar. So as a result, we have 0.55 molar at equilibrium. So it's important to just look out for the ratio, like the mole ratio for different equations. And now with our 3 final equilibrium concentrations, we can find our new KEQ. It's equal to our products, so 0.15 times 0.15 over reactants. And this is 0.041. Next, we have this equation here. It's in equilibrium, and the KEQ is given to us. And what we're trying to find here is the equilibrium concentrations. So this question tells us that initially we have 1 mole of H2, we have 1 mole of I2, and this is all in a 2-liter container. Okay, so what we have to do first is find the concentrations of these two reactants. So we know that concentration is moles over volume, so 1 divided by 2. So it's going to be 0.50 molar of H2 and 0.50 molar of I2. Okay, so now we know our initial concentrations. We can write our ice table. Initially we have 0.50, 0.50, and initially we don't have any products. So now what can we do? Well, we don't know how much is going to change, and we don't know what the final equilibrium concentrations will be, but we do know the KEQ, and that's going to help us out later. So what we can say for now is the change is going to be, we're going to minus some number, so minus x. So these are going to minus x, and then as the concentration of the reactants go down, the concentration of the products will go up. But since we have a 2 as a coefficient, we're going to be plusing 2x. So finally, we have 0.50 minus x, 0.50 minus x, and then 2x. Now we have expressions for each of the equilibrium concentrations. All we have to do is solve for x. So we can start by writing our equilibrium constant expression. That's going to be concentration of the products raised to the power of the coefficient over the reactants. And this is equal to 2x squared over 0.50 minus x. And since they're the same, I could square that too. And it tells us that KEQ is 50, so it's equal to 50. I'm not going to show you how to do the math, but if you solve this, x is equal to 0.39 molar. And from that, we can find the final equilibrium concentrations using these expressions. So concentration of H2 is equal to the concentration of I2, which is equal to 0.50 minus x, which is 0.39, and that should give you 0.11 molar. And then concentration of HI is equal to 2x, so 2 times 0.39, which is equal to 0.78 molar. And there's your answer. Okay, for our final example, we have this reaction here. It's in equilibrium, and we are given the initial concentrations, and we are also given KEQ. And what we're trying to find out is which way will the equilibrium shift to achieve equilibrium if these are the initial concentrations. So we want to know what the change is. So how do we do that? So how we do that is by doing what's called a trial KEQ, or you could call it Q. And I'll explain how we do it, but first let's just find what trial KEQ is. And we do that by taking the initial concentrations and doing a KEQ calculation with that. So it's going to be equal to concentration of N2 times concentration of H2 to the power of 3 over concentration of NH3 squared. So that's equal to 0.50 times 0.40 to the power of 3 over 2.5 squared. And that gives us 0.0051. So now we can find out which way the equilibrium will shift to achieve equilibrium. So what we do is we compare our Q and our KEQ. So which one is bigger? We can see that Q is clearly bigger than KEQ. So what the system is going to do is trying to decrease Q to turn it into KEQ. So we look here. If we want to make KEQ go down, what do we have to do? We have to decrease the products or increase the reactants, right? So how do we do that? We do that by shifting to the left side. Then you'll have less products and more reactants. So you can move towards the KEQ, which is smaller than what it is in the trial KEQ. So the equilibrium will shift towards the reactant side until KEQ is equal to Q, which is our trial one. Okay, hopefully that was understandable, and thank you for watching my second video. You can leave any questions in the comments.